Hi grade 11 chemistry students, welcome to another video lesson. This one's going to be on empirical formulas. Here we go with empirical formulas. Empirical formulas are formulas for compounds where we have the lowest number of atoms that still achieve a ratio of atoms that we're looking for. So for example, here we are with formaldehyde. Formaldehyde is, its formula is 1 carbon, 2 hydrogens, and 1 oxygen. So formaldehyde, it's actually already in its empirical formula format. So the empirical formula for formaldehyde is CH2O. Acetic acid, though, has a formula of C2H4O2. That has an empirical formula that is equivalent to formaldehyde's. It's CH2O. In other words, if we multiply the number of carbons, over here, if we divide the number of carbons in acetic acid by 2, divide the number of hydrogens in acetic acid by 2, and divide the number of oxygens in acetic acid by 2, we end up with CH2O. This one over here, same thing. Erythros, its empirical formula is CH2O. Glucose, divide by 3, we divide by 6 and we get CH2O. Hydrogen peroxide, H2O2, it has an empirical formula of HO because we can divide both atoms by 2. Okay, so this can only happen with molecules. We don't do this for ionic compounds. For example, if you've got sodium chloride, if you actually looked at the matrix of sodium and chloride bonded to each other, you know that you'd be able to pick out 2 sodiums and chlorines which happen to be bonded to each other, but we don't write the formula out as Na2Cl2. We'll keep it as NaCl. We wouldn't write it out as Na4Cl4. With ionic compounds, we always keep it in its lowest number of atoms in the formula. Okay, so there's your definition for empirical formula. Empirical formula, it's a formula that shows the smallest whole number ratio of the elements in the compound. Okay, so for example, CH2O or nitrogen with 2 oxygens. Empirical formula. Molecular formulas, on the other hand, would be a formula that shows the actual number of each type of atom in a molecule, not necessarily the lowest number of atoms to achieve the ratio between the elements. So C6H12O6, for example, you could divide each of those subscripts by 6 and you would get an empirical formula. N2O4, you could get an empirical formula if you divide those numbers by 2. But those are molecular formulas that we're looking at. So what do compounds with the same empirical formula have in common? They have a ratio of their elements which is the same, and that's it. Nothing else. Materials with different molecular formulas but the same empirical formulas will be completely different in terms of their material properties. For example, formaldehyde. So here it is. There's the picture of it. Formaldehyde, CH2O, it's a preservative, whereas lactic acid, C3H6O3, same empirical formula as formaldehyde, but it's something that's found in tired muscles after glucose has been broken down. And you can see here, it is a completely different molecule. It's got a different shape, it's got a different number of atoms, etc., etc. Looking at glucose, C6H12O6, that's what's used in cellular respiration as fuel so that we can obtain energy for cells. And again, here the shape of the molecule is much different. It's a bigger molecule. So we're seeing for all these different materials with the same empirical formula, the molecules are different sizes. They may be different shapes. Because they're different shapes and different sizes, they possibly have a different degree of polarity for that molecule, and they possibly will have, when they come together, different degree of London forces between the molecules. And of course, as you know, that has a big effect on their material properties.